When engineers build payment integrations, they often design them for perfect conditions. They assume the physical world behaves exactly like a synchronous digital API. But out in production, highly structured state machines collide with unpredictable physical events, causing rigid logic to break. To understand how Stripe issuing handles this collision, we have to look at the strict conceptual split at the core of the platform, the difference between an authorization and a transaction. An authorization is a conditional hold on funds. This is the stage where you have control. The developer's predefined spending limits and real-time authorization logic govern whether this hold is approved or declined. A transaction, specifically a capture, is the definitive, immutable ledger event. It permanently deducts the purchase amount from the balance you use for issuing. Once an authorization is approved, captures always succeed. The spending controls and card status checks that dictate your authorizations do not apply at the capture phase. To build a robust issuing integration, developers must treat the API documentation as a map of state transitions designed specifically to absorb physical world anomalies. In the standard sequence, an approved authorization is captured within 24 hours. The status flips to closed, releasing the hold as a new capture permanently moves the money. Hotels, airlines, and car rentals, however, can capture up to 31 days later. The complexity increases when funds move in the opposite direction. Refunds are logged as transactions where the type key is explicitly set to refund. Merchant networks do not consistently tie refunds back to the original payment. Because of this structural gap in the credit card network, linking a refund to its parent authorization is an inexact science. For unlinked refunds, the authorization field is set to null. Stripe processes these identically, crediting your balance even if the card is inactive. For refund reversals, correcting duplicate refunds, the amount displays a negative integer, though the type remains refund. Developers can verify their system's resilience to these edge cases by generating simulated payloads using the Create Unlinked Refund API test helper. Hard-coding your database logic to require a parent authorization for every incoming credit will crash your ledger the moment a legitimate, unlinked merchant refund arrives. The final transaction amount will frequently diverge from the initial authorization amount. A partial capture occurs when a merchant captures less than the 5,000 cents authorized. Stripe holds the exact difference. Conversely, an overcapture occurs when the final amount exceeds the authorization, like when restaurants add a tip or taxis drive further than estimated. Overcaptures are a standard authorizational requirement for these specific merchant categories. They are fully legitimate network events and cannot be hard-blocked by issuing controls. Airlines and e-commerce platforms utilize a multi-capture model. They authorize the total purchase once, but capture fractions of the funds multiple times as individual items ship. A single purchase handled this way generates a cascade of multiple issuing authorization.updated webhook events. You can stress test your backend against this behavior by calling the Authorization Capture Test API and setting the parameter Close Authorization to false. If your backend reconciliation script relies on a single final capture that perfectly mirrors the authorized amount, routine events like split shipments and restaurant tips will silently corrupt your user balances. The most radical departure from digital state logic is the force capture, where money moves without any corresponding authorization. Consider an issuing card swiped on a commercial flight. The point-of-sale terminal on the beverage cart has zero internet connectivity. Because the terminal is entirely offline, it cannot request an authorization from the network. Instead, it batches the raw transaction data and pushes it to the network hours later when the plane lands and reconnects. In a force capture, Stripe creates the transaction and deducts the balance immediately. The type is capture, but authorization is null. This identical payload structure appears if a merchant forces a capture on an authorization your system explicitly declined. Stripe cannot programmatically block force captures because many of them, like the offline in-flight purchase, are entirely legitimate and structurally required by the network. If a force capture is the result of fraudulent behavior, the only mechanism to reverse the ledger event is human intervention through the formal dispute process. Developers cannot strictly gate outbound money movement behind an authorization object. When physical terminals lose their signal, the payment network simply bypasses digital gates. These payload anomalies affect the broader Stripe financial ecosystem, particularly for platforms integrating Stripe Treasury. This architectural topology map shows transactions captured or refunded to a Treasury financial account require distinct routing logic. The Treasury field links to received debit for captures or received credit for refunds. Balance impacts reflect entirely on Treasury transactions. Standard balance transactions don't exist here. Across all of these scenarios, the assumption of a pristine one-to-one relationship between an authorization and a capture is an architectural anti-pattern. Systems must be written to handle null authorizations on both inbound refunds and outbound forced captures. They must correctly process negative refund amounts and mathematically reconcile captures that aggressively vary from their parent holds. A production-grade Stripe issuing integration succeeds by engineering a state machine flexible enough to absorb the unpredictable chaos of the global physical economy.